Bayes classifier for Gaussian distribution. This was a topic which I intended to cover up last time itself in the last lecture, but due to insufficient time we couldn't. So today we are going to first discuss upon this. In fact, I mean, although this is the title given to the lecture, I think that I am going to spend roughly half the lecture on this, and then I mean, in the remaining part of the time we will go over to the discussion about the multi-layer perceptron, and I mean, to the extent time permits, we will be discussing about the backpropagation algorithm. Okay. Now, in the last class we were discussing about the Bayes classifiers, okay, and in fact one point which you must have noted is that the Bayes classifier's computational part only involves the computation of the log likelihood ratio, okay, or rather to say the likelihood ratio is the thing that we are I mean first computing, okay, in terms of if fx x given c1 and f of x given c2, okay, the ratio of these two gives us the likelihood ratio, and then we took the log likelihood ratio, okay, and this log likelihood ratio was compared with another factor called xi, which was defined as the threshold. So if the log likelihood ratio is greater than the threshold, okay, we were classifying it into one of the classes, let's say C1, and if it is otherwise, then we were classifying it into the other class, that is C2. Okay, that was the simplest kind of an approach that we had taken, and in fact our intention was to show that for a Gaussian distributed patterns, okay, we are going to show that the Bayes classifier is going to act very similarly to what a linear perceptron does. Okay. In fact, this is a very interesting result that we are going to talk about. So, again we consider a two class problem, right, that it is going to classify it into either the class C1 or C2, okay. And another point that we should keep in mind is that all the vectors that we are deciding, I mean that we are discussing about, in fact we are taking the x vector, the capital X vector, to be a random variable, okay, out of which we are taking instances as the small x vector, okay, and we have considered that this x vector is an m dimensional type, so that whenever we are considering an m dimensional space, I mean like say for example here if we draw any imaginary m dimensional space, okay, and supposing this is the space in which the x vector, that is the random variable, can reside, then the instances of the small x vector that we are going to have will be, I mean let us say that this is the mean vector, okay. Now most of the vectors, okay, I mean the belonging to this random variable would be distributed close to this mean vector, and as we move away from the mean vector, okay, their population will decrease. So that is why the use of the probability density function, the PDF, is coming into play, and we are assuming the PDF distribution to be a Gaussian distribution in this case, right. So let us consider a two class classifier problem where for the class C1 we are going to have the expectation of this random variable x, okay, capital X, okay, that will be equal to what? That will be equal to the mean, okay, that will be equal to mean, and in this case mean a scalar or a vector? Definitely a vector, because all the instances of this random variable x, they are vectors. So definitely when we are talking of a mean, the mean is also a vector, mean is also an m dimensional vector. So we call this mean vector as the mu1 vector, okay. And then another I mean statistical parameter that we always consider for the case of scalar things. What we consider is the variance, because that shows the dispersion of the data with respect to its mean. Okay, that's how we calculate that if the data is much dispersed from its mean, then it shows a large variance, whereas the data which is closer to the mean, data distribution which is very close to the mean, that will show a smaller variance. Now, variance in the case of a scalar variable, the variance was also a scalar quantity, but in this case the variance that we are talking of is also not a scalar. Variance has to be in this case vector. Definitely it is in fact of a matrix type, because the matrix should indicate, okay, the dispersion not only with reference to itself, okay, which will be indicated by its diagonal elements of the matrix, but also the off diagonal elements which will basically show the correlation between the data with its other elements. Okay. So, basically we are going to form a matrix which is called as the covariance matrix, which is going to be the equivalent of the the variance that we are having for the case of scalar data. So, the covariance matrix that we are talking of should be defined in this manner. Okay. So, it should be the expectation of x minus mu 1, all in vector notations, okay, times x minus mu 1, okay, in this case transpose. So, if we make it a transpose, okay, we are taking an outer product of it. So, by taking the outer product, we are going to get a matrix, and that matrix we are going to call as the matrix C, which is nothing but the covariance matrix. So, this is the covariance matrix, right. And very similarly for the case of class C2, we are going to have the expectation of x vector to be equal to mu 2 vector, and the expectation of x minus mu 2 vectors, outer product with x minus mu 2 transpose. Okay. This is also taken to be C, assuming that the covariance characteristics, okay, is uniform throughout the entire space H that we are talking of, because out of C1 we are taking the sample space to be, we are taking only a subset of that H1 from which we derive the training samples for C1. Again, likewise H2 we take a subset of C2, and then we were defining in the last class the whole set H from which we were considering. So, assuming that the variance statistics remaining the same for that, we can denote it by the same C vector C matrix, which is the covariance matrix. Okay. Now, another point to be noted is that this covariance matrix C is non-singular, okay, and so its C inverse, okay, exists. All right. So, now we are going to define a Gaussian distribution for both the classes, fx x given C1, also fx x given C2, both these distributions should be Gaussian, and the Gaussian formula is very well known to us. We have been dealing with such formulas almost in all the subjects. Okay. We are having Gaussian distribution as a typical normal distribution case. Only thing is that in this case, okay, our data will be a little more complicated, in the sense that we are going to have m dimensional type, right. The Gaussian distribution is going to be m dimensional. So, let us write down the Gaussian distribution expression considering an m dimensional case. We are going to write as fx x given Ci, that is equal to 1 upon 2 pi, in this case it will be m by 2, 2 pi to the power m by 2, m is coming because of the dimensionality that is involved, in this case it is m dimensional, and then instead of the 2 pi sigma square, you remember that we have root over 2 pi into sigma square, that sigma square term will be in this case replaced by the determinant of c, okay, determinant of c, and this whole thing to the power half, okay, and then the exponential term that will be existing is, I mean, I am not writing the exponential term here because I need some more space for it. So, it should be exponential to the power minus half x minus mu I. So, here I am putting as C I, so that this will be valid for I is equal to 1 and 2 class problem, because it is. So, this is x minus mu y transpose C inverse x minus mu y. Okay. So, I think we have understood the form. This is a quadratic form of the expression. So, this is in other words the, I mean, equivalent of the expression that we are going to have for the one dimensional case or the scalar case. Okay. So, this is with the knowledge that m is equal to the dimensionality of the observation vector vector x. Okay. Now, we can make, I mean, some further assumptions, okay, and there is nothing wrong in it. Firstly, that we are going to have two classes C1 and C2, okay, although in the last analysis we have assumed the two probabilities to be independent, P1 and P2 we took. So, where P1 and P2 could take any values, okay, but I mean, we can always assume that the two classes are equiprobable. In most of the cases it may be like that only. Okay. So, if two classes C1 and C2 are equiprobable, in that case we are going to have, so two classes C1 and C2 are equiprobable, in which case we can obviously write that P1 is equal to P2 is equal to half, okay, and also we can write down, I mean, some problem with the sketch pens anyway. Yeah, this is better. So, C12 is equal to C21, okay, I mean the cost functions that we had taken last time. C12 and C21s are what? They are the cost functions which are associated with correct, incorrect classifications. So, C12 and C21 they are the incorrect classifications cost function, and C11 and C22 they are the correct classification cost functions, which there is no reason why we shouldn't I mean take it to be 0, because we said that those cost functions should be as minimum as possible, as low as possible. So, there is nothing wrong if I assume that C11 is equal to C22 is equal to 0. Okay. So, if we have that, okay, and if we try to take the likelihood ratio, because in order to take the likelihood ratio, what we have to do is we have to first write the expression for C1, x given C1, then we have to write it for x given C2, and simply we have to take the ratio of these two, and you can very clearly see that if you are taking the likelihood ratio, then this coefficient term will get cancelled out, they become 1, and only the quantity written within the exponential will remain, okay, exponential to the power something by exponential to the power something, which will mean that exponential to the power, the expression that we are going to have for mu 1 and the expression that we are going to have for mu 2, they will be just subtracted from each other. I mean, if we are assuming the fx x given C1 by fx x given C2. Okay. Now, because the quantity that we are getting as a likelihood function is everything written within exponential term only, okay, the most logical thing will be to take a natural logarithm of both the sides, right. Natural logarithm of the likelihood function, which we are going to call, I mean, which we have been calling so long as the log likelihood ratio. So, the log likelihood ratio, whenever we take the natural logarithm of both the sides, it will be log likelihood ratio on the left hand side, and the right hand side exponential right hand side term involving the exponential will then become a straightforward term. It becomes a linear term in fact. So, if we take the natural logarithm of the likelihood ratio, okay, we can write down this expression directly, that the log of the log lambda x vector, okay, that is the log likelihood ratio, it is going to be equal to minus of half x minus mu 1, okay, transpose C inverse x minus mu 1, all right, plus half of x minus mu 2 transpose C inverse x minus mu 2, right. So, the mu 2 term, and from that we subtract the mu 1 term, okay. So, simply the ratio of f x x given c 1 and f x x given c 2, taking the logarithm of both the sides. Okay. So, this could be simplified further, and if we simplified it, then we will see that we will get two terms here. One is mu 1 minus mu 2, this transpose C inverse x vector plus half of mu 2 transpose C inverse mu 2 minus mu 1 transpose C inverse mu 1, all right. And what is going to be log xi in this case, because we are assuming P1 and P2 to be equal to half and C12 and C21 to be equal, okay. Just have a look at the earlier class note, there you will find that xi term will be equal to 1. So, that in this case log xi is simply equal to 0. So, in that case what is going to be the boundary, what is going to be the decision boundary? The decision boundary should be when log of lambda x, the log likelihood ratio is greater than or equal to log xi, in this case 0. So, when this expression is greater than or equal to 0, have you got it what we are wanting? Is it linear? It is very much linear. You see that this involves, if you look at the addition terms of these two, okay, there are two terms that is involved over here. One is a term involving x and a term which does not involve x, which is independent of x. So, the term that is independent of x, that means to say this mu 2 c 1 c inverse mu 2 minus mu 1 transpose c inverse mu 1, okay, this term that we have got is independent of x, and you could imagine that this is like the bias. This can be substituted for the bias b, and if we now substitute this for the W transpose, okay, in that case what is the expression that we are getting? We are getting, and if we call this to be y, in that case the equation that we are getting out of this log likelihood ratio for the Gaussian distribution based classifier is simply y is equal to W t x vector plus b, which is the equation of, so this is equal to this. So, that means to say that the decision boundary equation is W transpose x plus b greater than or equal to 0. This is the decision boundary, which is the hypersurface equation and which is our simple perceptron equation. So, we started with Bayes classifier under Gaussian distribution assumption, and we landed up in a form, okay, classification decision boundary solution that we are getting out of it is exactly the way the decision boundary problem is for the perceptron. So, the analogy that we were talking of since the last class about the Bayes classifier and the single layer perceptron very much holds good. Okay, so, I think you should now feel convinced that there is a very strong analogy, a very strong similarity is indeed there, okay, but come to think of it in a more deeper way, you can realize that there are some striking differences also, in addition to whatever resemblance we have got in terms of this decision equation. Number one, that when we talk of the perceptron, okay, the first basic fundamental assumption that we are making is that the two classes C1 and C2, they are linearly separable. Not only separable, they are linearly separable. But the Bayes classifier problem that we have defined here, okay, is based on the assumption that the distribution is Gaussian. The distribution of the two classes, they are Gaussian in nature. And even if you have mu1 and mu2 to be much separated from each other, okay, let us say for example, I mean I cannot, since I cannot sketch a Gaussian distribution for multidimensional, any m dimensional case, I can at least sketch for a single one dimensional case of Gaussian. So here let us say that this is mu1 and let us say this is mu2, widely separated, and also I assume that as compared to their distance of separation mu2 minus mu1, their variance is also relatively of smaller magnitude. Even then also the distribution which could be plotted something like this, okay. If this is the kind of the distributions that we have got, this being the distribution of class C1 and this being the distribution for class C2, okay, they are in strict sense not at all overlapping. I mean they are not at all non-overlapping as the linear classifier would require, I mean as the perceptrons would require. That is a fundamental condition of perceptron, that the pattern classes must be linearly separable, but in this case the pattern classes are theoretically overlapping, no matter how far you drive them away, okay, mu1 and mu2 you drive them away, and however small C1 and C2 you can use, okay, still they are overlapping to some extent. And the thing is that, so naturally there lies a very fundamental difference, that here this is not I mean linearly separable problem. So Bayes classifier can solve it, perceptrons cannot. Okay. Again, Bayes classifier for the case of Gaussian distribution only is getting converted into this type of a linear form. If you are taking distributions other than the Gaussian, then this relationship will not hold good. Whereas in the case of perceptrons, this relation always holds good, because perceptron does not make any underlying assumption about the probability density functions of the classes. Am I right? So that is why the I mean perceptron we can say is non-parametric. Okay. So we can in fact I mean just jot down a few points about its comparison. Okay. Most of it we already discussed. Okay. Comparisons between Bayes classifier and perceptrons. Number one comparison is that perceptron requires linear separability, whereas Bayes classifier with Gaussian PDF are non-separable. They are absolutely non-separable class. No question of linear separability, they are absolutely non-separable. Okay. The second is that perceptron convergence is non-parametric. Non-parametric means it is not dependent on the underlying distribution, underlying probability density function. Okay. whereas Bayes classifier is indeed parametric, because it is under the assumption of Gaussian that it is linear. Okay. And then the third point is that the perceptron convergence algorithm is adaptive. And simple to implement. Whereas the design of Bayes classifier is fixed, because in this case design of Bayes classifier is very much dependent upon the log likelihood ratio that we are computing. So, it is fixed. Okay. You can make it adaptive, I mean when its statistics changes, but then you have to have a very large memory to track down its statistical behavior. That means to say, what you have to do is to track down its mu2, I mean mu1, mu2, see the covariance matrix variations. Okay. Unless you do that, you cannot make the Bayes classifier to be adaptive. So, these are some of the I mean dissimilarities, okay, that exists, okay, and only under the linear case that, I mean only under the Gaussian distribution case that the Bayes classifier with Gaussian PDF is very much similar to the way perceptron behaves. But if the underlying distribution is indeed Gaussian, if the two classes of patterns are Gaussian distributed really, and if we want a perceptron to solve the problem for that, then there lies a problem. Like say for example, if this is a kind of problem that we give to a perceptron for a solution, then although the ideal decision boundary could be somewhere over here, okay, but this decision boundary is certainly going to shift, because whenever you are trying to achieve a perceptron convergence, because it is not linearly separable, the two classes are not linearly separable. So, that is why it will not be able to find any fixed decision boundary. If you are iteratively trying to converge a perceptron algorithm, the decision boundary will shift in and around this region, it will oscillate in and around this region and never obtain any direct solution of the decision boundary. Okay. So, this much is the discussion that I wanted to have on the broad chapter of single layer perceptron, and in fact, this chapter we should end up with some amount of historical note in it. In fact, I mean there is some historical note background which I had given to you earlier, but just to re-mention it and also to rethink about it in terms of the multi-layer perceptron, which we are going to discuss shortly. The thing, as I have already told you, is that these theories related to perceptron, the theories related to the least mean square algorithm, they were all developed in the 1950s, and the perceptron theory was actually proposed by Rosenblatt in the 1950s, right. Now, in the 1960s, actually it was, I mean after Rosenblatt's theory was presented, it was Minsky and Selfridge, okay, these two people, these two scientists, okay, in the year 1961, all right, they had presented a paper where they had shown that the inadequacies of perceptron, in the sense that perceptron cannot solve problems, okay, which are not linearly separable. In fact, they were the first to demonstrate the incapability of perceptrons to classify the exclusive OR kind of a problem. The simple binary exclusive OR problem could not be solved, this was shown, but subsequently it was argued that, so I mean in this sense Minsky and Selfridge were very much right. I mean they had very, I mean made a very timely contribution that, I mean saying the inadequacies of perceptron, and then when it was felt that perhaps perceptron's limitations might be overcome if one uses a multi-layer perceptron. A single layer perceptron's limitations could be overcome by multi-layer perceptrons, and when theories like that were proposed, okay, that time, I mean, Minsky and Peppert, okay, Minsky and Peppert, these two scientists, okay, they in the year 1969, they published a book, a very well known book, a classical book named as Perceptron, in which book they pointed out that the inadequacies of single layer perceptron definitely exists, and one has to accept that. In fact, I mean, people who first proposed the theory themselves accepted, there was no reason why they shouldn't have, but they were highly skeptic about the performance of multi-layer perceptron, because Minsky and Peppert directly asked them that if the problem like this is not solvable by single layer perceptron, how can you expect to solve it, get it solved by multi-layer perceptron? Okay. And very brilliant scientists as they were, okay, there was a thinking in the, I mean, thinking and rethinking in the neural network research community about the whole success of neural network, because anyway, I mean, neural network has to sometimes solve problems which are separable, but which are non-linearly separable. So, if neural network cannot solve non-linearly separable problems, okay, then there is no use of neural networks. In fact, following the book by Perceptron, by Minsky and Peppert in 1969, there was I mean, very much subdued research activity on the neural networks. Okay. In fact, for the next 10-15 years, not many people talked much about neural networks. I mean, especially the perceptron and the multi-layer perceptron model, people thought that maybe that this is something which was not very successful. It was proposed, but not very successful. But in the year 1986, okay, it was two scientists again named Rumelhart and McClelland. Okay. In the year 1986, they published a book which is named as Parallel Distributed Processing. Okay, just observe the name of this book. Okay, we hear about a subject, a very popular subject called parallel and distributed processing, but mind you, here the name that is given to this book is Parallel Distributed Processing. There is an omission of and. But I mean, the whole thing that they tried to talk about in this book is that neural network is definitely a parallel computational model, no doubt about it, because you can employ several neurons, okay, and you can do the processing independently. They are independent, they are indeed distributed, because those neurons need not be distributed in one single place. The neurons could be distributed in several places, okay, they could be distributed. So, it is the parallel distributed processing that was proposed by Rumelhart and McClelland in the year 1986. Parallel distributed processing book was written, and that was the first book in which after which the concept of multi-layered perceptrons were popularized. Okay. In fact, they are the first people to coin the term of back propagation. Okay. In fact, I mean, lot of times I find that the word back propagation and multi-layered perceptrons, they are very much interchangeably used. It should not be very much interchangeably used, because back propagation, this word itself has got some concept built into it, okay, whereas coming to think of multi-layered perceptron, the idea is pretty simple. What is meant by multi-layered perceptron is that instead of only the input and the output layer, the way we have it for the single layer perceptron, we are going to have a layer in between which is called as the hidden layer, right. So, the multi-layer perceptron architecture would look something like this. Okay. there will be an output layer. Okay. So, this will be an output layer, there will be a hidden layer. I might have told, I mean given this diagram sometimes or the other, I mean while discussing other things, I must have talked about this. So, there is nothing great about this diagram, but one thing that these hidden layers are fully interconnected to the layer that is preceding it. In fact, all the layers starting from the output up to the layer immediately before the input, it is fully interconnected to the layer which is preceding it, which means to say what? That if we are talking of this, then it is fully interconnected to all the hidden layer neurons. Like this is going to happen for all of these output layer neurons, right. Okay. Like this it goes on. I mean I am not completing this diagram. Again here this should be connected to all the neurons in the previous layer. Now, in this example I have shown one input layer, one hidden layer and one output layer, but generally speaking you could have more than one number of hidden layers also, but the very fact that it is a multi-layered perceptron, okay, because it is multi-layered perceptron, it must necessarily have at least one hidden layer, right. Now, the thing is that having told about the multi-layered perceptron, I think it is very much necessary to talk about what the term back propagation actually means, because I have seen that some people have got certain misconceptions about the back propagation, and I have heard some people wrongly talking that as if to say that okay, back propagation as if tries to mean that like there is a forward signal flow, which will be there. In fact, what happens is that this input will be having some signals associated with it, and these signals will come to the next layer, in this case hidden layer, which will be. So, there will be some linear weighted inputs that you will get, okay, which we are going to call as the induced field, that is to say sigma of Wji. If you call this to be the neuron j, then sigma Wji xi, where I is equal to 1 to m. I mean if there are m dimensions in the input, okay. We were describing the linear activation to be that, and then we were following it up with the activation function phi of v, that is what we were taking, which was in fact doing some kind of a hard limiting and things like that. Now, there is a forward signal flow. In this case, if you observe, okay, the signal will first flow from the input layer to the hidden layer, and then the outputs of this hidden layer will then influence the output neurons, right. So, as if to say that the signals are propagating in the forward way. Now, some people wrongly believe that back propagation means that as if to say you have got a feedback mechanism in the connection, and the connections are bidirectional, and some signal also flows from output to the input, which is not very correct. In fact, the word back propagation is to be used very cautiously, that here back propagation means that it is back propagation of errors. Okay, please note that it is back propagation of errors, so that in the forward signal flow path, in the forward path we have got only the signal flow, and in the reverse path, okay, we are going to have the computation of errors. Because one thing is to be understood at this stage, if you are again bringing in the analogy of single layer perceptrons, there try to remember what we did. In single layer perceptron, we were considering a neuron which was connected to several inputs, and then it was generating some output, let us say y, and then there was a desired output which was d, and we were feeding as a pattern set, we were feeding the x vector as well as the d as the training patterns, and this y minus d, or that was the error term for us, using which we were directly modifying the synaptic weights here. Now, if we try to do the same in the case of multi-layered perceptrons, how are we going to achieve it? Because okay, here there will be some final output, let us take any one output neuron, there will be some output, let us say y, or if this is the jth output neuron, let us say there will be some yj, there will be something desired which is dj. So, accordingly there will be some error ej which is yj minus dj, but that error can influence, or using that error we can update the weights that are connected between the excuse me, that are connected between the output and the input which is immediate, I mean and the layer which is immediately preceding it. But if somebody asks me the question that is well and fine, you can adjust the weights belonging to this layer, but how about weights belonging to this layer? I cannot do it, because in order to adjust the weights over here, I have to get an equivalent picture, that as if to say that I know that what this output should have been, what the equivalent desired output should have been at this stage. Only if I had known that the actual output and the equivalent desired output which should have been at this stage, only then I could have computed the error, and only if I could compute the error, I could adjust the weights at this layer. And like that I have to go back to the preceding layers, because there may be more than one hidden layer of neurons. So, like that I have to go to the preceding layers of neurons, and I would find out that what should be the weight adjustments that are needed in the preceding layers, right. So, there what we are going to do is that the error that we are getting, this error should be computed in its equivalent form in all the previous layers, okay. And that is the whole idea of the back propagation of errors. So, when we talk back propagation, again mind you, be careful in using the term that it is back propagation of errors. In fact, it should look something like this, that let us say that we have got 3 neurons, okay. Let us say these are the last hidden layer, okay, the hidden layer that is closest to the output layer. This is an output layer neuron, let us say, connected to 3 hidden layer neurons. So, that here we are getting the signals from these 3 neurons, and then here we are getting the inputs, okay, and we are going to get the outputs, I mean we are going to have, yes, I mean the output will be here. So, all these lines that I am drawing with firm black lines, they are nothing but the function signals, okay. So, these are the function signals, and then the error signals would be shown like this. So, we first compute the error here, I mean at the output layer, and then we have to propagate these errors backward, okay, up to the level of the immediate before, I mean immediately preceding hidden layer. And then once here the errors are computed, then this error should be further back propagated, okay. So, this is the flow of the error signal. So, what I am drawing with this color is the error signal, which is by back propagation, okay. So, this is the concept. Now, let us go over to the beginning of the back propagation algorithm. Now, the beginning of back propagation algorithm would look very similar to the weight updating equation, or what we called as the delta rule for the case of single layer perceptron, the analysis and everything would look very similar to that, but only thing is that we will realize the difference when we come back from the output layer to the preceding layers. When we come to that and we calculate the equivalent error signals, there we will understand the difference between the approach that we had followed so far for single layer perceptron and the approach that we are going to follow for the back propagation. So, the approach of back propagation would start in a very similar way. Okay. So, let us consider an output neuron J. Okay. So, we consider neuron J at the output, okay, and we consider the iteration number to be n. So, we consider the iteration n, and here iteration n means it is the presentation of the nth pattern. Okay. So, if we take the approach of the LMS algorithm, there what you did, you remember, there we were considering the instantaneous error energy and we were minimizing the instantaneous error energy and updating the weight for every n. That means to say that we were not waiting for one complete set of patterns to be presented. In fact, one complete set of patterns is called as epoch. Okay. So, there we were not waiting, epoch is one complete set of patterns. So, instead of waiting for one complete set of patterns or an epoch, okay, we were updating the weights with the presentation of every training sample. That is what we were doing for the case of LMS, because we were considering only the instantaneous error energy. Okay. We were only considering what Ej at iteration n square of that. Okay. So, here also we are going to follow the similar approach, as if to say that with every presentation of the pattern we are going to update the weight, and later on we can show that whether that becomes equivalent to updating the weight once for all for one complete epoch. Okay, because if you are updating the weight after one complete epoch, then you have to calculate the average error energy. I mean, that should be based on the average error energy, whereas doing it for every pattern means based on the instantaneous error energy itself we can do it. So, now the error signal of the, I mean at the output of the neuron J could be written very simply. So, the error signal at the iteration n we are going to write as Ej of n, which should be equal to Dj of n minus Yj of n. Now, here because I am having more than one neurons at the output layer, so that is why I am numbering or indexing the neurons as such. So, that is why we are saying Yj Dj. So, everything is pertaining to the jth neuron, and the error signal is as follows. So, what is going to be the instantaneous value of the error energy? The instantaneous value of the error energy is simply going to be E of n equals half of what? Ej n square. But I said there are more than one outputs. Okay. So, definitely we have to sum up, even if we are talking of instantaneous value of the error energy at the nth iteration or the presentation of nth pattern, whatever errors are existing at the outputs of every neuron or every output neuron, they must be summed up. So, we should sum it up over J, J belonging to the output layer. So, if we say J belongs to C, where the set C includes all the neurons in the output layer. Okay. So, having defined this, okay, the average squared error energy, I mean if we try to think of the average, okay, then I mean if there are capital N number of total training patterns, let us say, okay, if there are n number of capital N number of training patterns, then the average squared error energy that is E av n is equal to 1 upon n summation of E n. E n is what I have defined just now, okay, the instantaneous value. So, if this instantaneous value of this error I sum it up for n equal to 1 to capital N, where capital N is the total number of training patterns, total number of training patterns, that is one that composes one epoch. Okay. Now, there could be two different approaches. One approach is that on a simple pattern by pattern basis you update the weight, like the way we did for the LMS algorithm, or the other approach could be that you calculate this average squared error energy, and based on this average squared error energy you adjust the weight once for all. Now, this in fact is going to be nothing but, I mean the minimization of this average squared error energy is just going to be an estimate of what the average weights that we are going to get out of this. You see here, if at every iteration we minimize, I mean for every pattern presentation we minimize this E n functional, okay, then we are going to get an updated weight. So, then over n number of patterns, over capital N number of patterns, if we take the average weight, okay, that weight and this weight will not be exactly the same. I mean the weight that you are getting by minimizing this EF, that will not be same, that will be, there will be some deviation. So, the weight estimate that you are getting out of this is going to be some estimate of the true weight that you will get by following the instantaneous approach. In fact, we will, I mean there is nothing wrong in following the instantaneous error approach only. So, I can end this class of today because I am not being able to complete the total analysis because of lack of time today. In other words, what I can simply say is that the total output that I am getting out of this is, for the jth neuron, if I take the Vj at the nth iteration should be equal to summation of Wji at n times Yi of n, and you add it up for I is equal to 0 to m, where m is going to be the dimensionality. In fact, we added I is equal to 0 to m after embedding the bias term also into it. Okay. So, this is the complete term that we are getting as the induced local field at the input of activation function of neuron J. So, this is input of activation function of neuron J, okay, and this Yi's are what? Output of the previous layer. So, these are the output of the previous layer, and in the case of multi-layered perceptron it is necessarily the hidden layer, that immediately precedes the output layer. Anyway, with this knowledge, okay, we will continue our discussion about the derivation of the expressions for the back propagation of errors, which is going to be very important. In fact, that is the underlying theory of the multi-layered perceptron. and that we will do in the coming class. Thank you very much.